So this is the 8th problem in this series, and this is problem number 1.324. The problem is stating a horizontally oriented tube AB of length L rotates with a constant angular velocity omega about a stationary vertical axis OO dash passing through the end A. The tube is filled with an ideal fluid. The end A of the tube is open. The closed end B has a very small orifice. Find the velocity of the fluid relative to the tube as a function of the column height h. So just like all the problem of fluid mechanics, we are again going to begin the problem by drawing a necessary diagram of the situation which the problem is describing. So this is the situation which is described in this problem. And when we begin this problem, we begin by drawing or selecting an elemental mass at a distance x from the axis of rotation. So at a distance x from the axis of rotation, we select a patch of thickness dx, and over here we are considering cross-sectional area A. So the first thing that we write over here is the elemental mass that we have selected is having mass rho A dx. So if I consider or draw the FBD of this particular point which we have selected, then we can draw it in this way. That over here this dx thickness, is having pressure variation around it. So this dx thickness is such that it will be acted upon by a pressure P, resulting in a force pressure into area A, and on the other side we will have a pressure P plus dP multiplied by area A. Now the net force is balanced by m omega square r. So over here we can say that the net force on this elemental patch P plus dP multiplied by area A minus PA is equal to dm omega square x. So this is the expression that we have. So dP multiplied by area A is equal to rho A dx omega square x, and hence over here we can say dP is equal to rho omega square integration x dx. Now over here if we understand this part, then we can say that over here atmospheric pressure is acting as the problem is suggesting that end A is open and the end B is having a small orifice over here. So this point is at a distance L minus h from the axis of rotation, and the farther end is at a distance L from the axis of rotation. So the limit of integration is ranging from L minus h to L, and pressure variation is from P0 to P. So over here on solving we obtain P minus P0 is equal to rho omega square by 2 L plus L minus h, that is we will get L square minus L minus h whole square. So we are using the expression a plus b a minus b to resolve it to a simpler term. So we will get something like this. Over here we get rho omega square by 2 integration of x dx x square by 2. So L minus h and L, and then upper limit minus lower limit. So we obtain a expression like this. So over here we can write P equals P0 plus rho omega square by 2 2L minus h times h. So this is the expression that we have. Now the next thing that we need to understand is that at this point which we mark as point 1 over here and this point 2 over here, we are going to apply Bernoulli's expression. So at point 1 we have pressure P which we have evaluated right now. At point 2 pressure is P0. At this point, as it is about to leave over here, the velocity is at v1 equals 0 and velocity at 2 is v, which we need to determine for this particular problem, and they both are at the same horizontal level. So h1 and h2 in the expression of Bernoulli's expression will turn out to be 0, and hence we can say applying Bernoulli's equation applying Bernoulli's equation, we say that P1 plus half rho V1 square plus rho G H1 equals P2 plus half rho V2 square plus rho G H2. Now H1 and H2 are on the same horizontal level. P can be written as P0 plus rho omega square by 2L minus H multiplied by H is equal to P0 plus half rho V square. So from here, if we solve for V, we obtain V equals omega square 2L minus H times H square root. And if we write it in the way it is given in the text, we write it as omega H root over 2L by H minus 1. So this is the final answer for this particular problem that we have solved. Problem number 8 in this series.